Welcome to this NPTEL lecture on reflector antennas. In the last lecture, we were discussing about the various efficiencies. So, we have found out the directivity and we have written in the last class the directivity of the reflector system into various efficiencies. So, out of that we have written up to these. There will be other efficiencies later. Now, we have also found out the expression for spillover efficiency. So, I think if you remember, we have written the spillover efficiency expression as the directivity of the feed. And about the aperture efficiency, we have said that it is the product of three efficiencies: the illumination efficiency, the polarization efficiency and the uniform field efficiency. So, when we have assumed these two to be same, the illumination efficiency expression we have written as up to this we have done. Now, if in many cases the feed that the radiation pattern for that, power radiation pattern for that does not have a dependence on the azimuthal angle phi. So, if we say that g theta phi is independent of phi, then this equation readily gets simplified, because this d phi that comes out, this integration we can perform. So, this 2 pi comes out readily both in the numerator and denominator. So, I write that g theta phi is, if this is independent of phi, then you can further simplify this aperture illumination efficiency, that will be 8 f square by a square now g theta phi becomes g theta only. And these already, if you see, when we found the f by d ratio, so this expression can be related to f by d ratio. So, putting that, we can write that this 32, because f square by a square, from here I can write f by d square into this third bracket as it is, and that f by d ratio we have seen that can be written as 2 in terms of the angular aperture 2 cot square pi by 4 into this. So, this shows that the when we say that for here you see that G is equal to this. So, if we want to maximize gain, we want to maximize eta A eta S aperture efficiency into spillover efficiency product. Now, aperture efficiency is basically this illumination efficiency into these. So, for the time being these are put to 1. So, this efficiency is now shown to this. So, from here we can see that so the optimization that we can do. So, aperture efficiency can be maximized. Now, I can write that aperture efficiency can be maximized if we do two things. One is that we use small angular aperture, because you see that cot function of psi. So, smaller psi will give you more aperture efficiency. So, one thing is small angular aperture, and previously we have seen that if we take the G, the feed power pattern, that is proportional to sec 4 theta by 2, then also we can maximize. But the problem for this is if we take this choice, then the spillover efficiency gets increased, because that becomes a pattern which has much more radiation in the edges. So, that is why separately this illumination efficiency cannot be a thing. So, we can now we will have to find a function that which can maximize this. So, instead of taking sec function, now people have found out that we can have a better function, that suppose the feed radiation pattern is something like 2 n plus 1 cos n theta. That means, instead of sec 4 theta, we take cos theta some power for 0 to theta to pi by 2. So, in this zone, and 0 elsewhere. Now, this factor 2 n plus 1, that is chosen for a reason that we can see that if a feed has this power pattern, what is the total power radiated? Total power radiated by the feed that will be 0 to 2 pi, 0 to pi by 2, then g theta sin theta d theta d phi. Now, so if you do this, already it is g theta. So, this phi integration will come out, and if you evaluate this, because this expression is easy to evaluate, you will find that it will turn out to be 4 pi. So, this is the reason that total radiated power for this choice becomes this. So, with this choice we can now find out what is the feed directivity. dF will be 4 pi, then maximum of g theta by total power radiated. So, maximum of g theta cos n theta can have maximum value 1. So, that means it will be 2 n plus 1, and total power radiated just now we have calculated 4 pi. So, that cancels this, and the directivity becomes 2 into n plus 1. So, that was the idea that, so this now if you remember, if you see this spillover efficiency expression derived earlier, that spillover efficiency is in terms of df into this. So, we can put this value of df there. So, spillover efficiency becomes, with this value, spillover efficiency will, you can now you know the pattern. So, that means this g theta expression you know. So, you can put it, it will be 2 n plus 1 0 to 2 pi 0 to pi psi by 2 2 n plus 1 cos n theta by 4 pi into 2 n plus 1 sin theta d theta d phi. This can be easily integrated, and it will become 1 minus cos psi by 2 whole to the power n plus 1. This will be the spillover efficiency. And now also with this choice of g theta phi, what will be the illumination efficiency? Eta is 4 f square s square 0 to 2 pi 0 to psi by 2 root over 2 n plus 1 cos to the power n by 2 theta tan theta by 2 d theta d phi, this thing square divided by 0 to 2 pi 0 to psi by 2 2 n plus 1 cos theta sin theta d theta d phi. Now, this you can easily integrate, but in the denominator actually we will do something. So, let us see the numerator 2 n plus 1 4 pi square 0 to psi by 2 cos theta n by 2 tan theta by 2 d theta whole square, and in the denominator we write 2 n plus 1 into 2 pi, but in place of this the, so what will remain is 0 to pi by 2 cos n theta sin theta d theta. Now, here we will put the expression of spillover efficiency. So, this instead of this we will write eta s by n plus 1. Now, that gives us, you see, eta s eta I product, which will be easier for maximization. So, we can write that from here I can write eta I eta s is 8 f square by s square n plus 1 0 to psi by 2 cos theta n by 2 tan theta by 2 d theta whole square. So, this needs to be maximized. So, this people have further make it now this integral is a 0 for odd n and non-zero for even m. So, this can be written as cot square pi by 4, then its value people have evaluated that. So, only for n even this is non-zero. So, those values are 24 sin square pi by 4 plus ln cos pi by 4 whole square for n is equal to 2, 40 sin 4 pi by 4 plus ln cos pi by 4 whole square for n is equal to 4, 14 half sin square pi by 2 plus 1/3 1 minus cos pi by 2 whole cube plus 2 ln cos pi by 4 whole square for n is equal to 6 and 18 half sin square pi by 2 plus 1/3 1 minus cos pi by 2 whole cube plus 2 ln cos pi by 4 minus 1/4 1 minus cos 4th pi by 2, then this thing whole square for n is equal to 8, etc. So, these curves are available. You can easily put these curves as a function of phi. So, if you look at the diagram, this as a function of angular aperture, this shows this. So, you see that every curve has a maximum thing. So, for n is equal to 2, you are getting a maximum, I can say something around 130 degree aperture. So, if we take the angular aperture to be 130 degree, then we get for the n is equal to 2, it is gives the maximum efficiency. Similarly, for n is equal to 4, it is something like 110 degree. For n is equal to 6, it is 90, n is equal to 6 will be something like 90 degree, and for n is equal to 2 something like 80 degree, etc. Also, we can see that if we separately see the spillover efficiency, then it shows that spillover efficiency goes to almost 100% the more we give the n value, and that is obvious because what is n? Physically, if you look at this expression, what is n? N come from here, that more directed feed. Cos function you are making, suppose you have a cos function is generally this, but if you square it, it will be more peaky. That will the value will be let us look here, that if you have this, the more peaky thing will be something like this, make another factor that will be something like this. So, that means if I make it more directed, then the obviously spill over will be less. So, that is shown by this graph, that up to 8 if you take, then it is very readily at a very small angular aperture it goes to high. So, main thing is from there the joint one you can easily find out. So, from these two figure the designer chooses the angular aperture. So, and decides. Now, then while deriving all this, we have assumed that uniform field illumination in the aperture, but obviously with a cos to the power n theta type of excitation, there will be taper. So, what will be the taper, that also we can calculate, that what will be the amplitude taper in the field. So, let us say that we have chosen from this figure some optimum phi value. So, let us call it phi opt. So, we know that G phi opt 2, that will be 2 n plus 1 cos n phi opt by 2. So, we have already found out power density in aperture power density Pa in terms of the feed pattern. So, we can from that expression we can write now I am putting the value of this feed power pattern. So, once I know this, it is obvious that what will be the at the edge the aperture field. Please remember, this is amplitude pattern, field amplitude. No, this is power pattern. From that I am writing the field amplitude at the edge. This is power pattern, aperture power pattern. So, field amplitude at the edge, that means there my angle is this optimum. So, that will be proportional to root over Pa, and field amplitude at the center, that will be when this angle becomes 0. So, that we know you can put the in the cos 0 angle. So, root over 2 n plus 1 by inside bracket f square or outside f, whatever. So, we can write what will be the amplitude taper A edge versus center will be half cos n by 2 So, for n is equal to 2, from the graph we have seen psi opt is something like 130 degree. So, we can say this one, this is called aperture taper. That is, if you calculate, that will become minus 10.44 dB. Remember that this aperture taper, to calculate this dB, we have taken a 20 log, because this is a field. For n is equal to 4, the optimum angular aperture is from that graph 110 degree. So, taper is minus 11.74 dB for n is equal to 6. This from the graph is almost 90 degree. So, amplitude taper, this is minus 16.42 dB, etc. Also, you can find the corresponding taper at the feed radiation pattern. So, feed power taper, because the designer of the feed needs this value, that will be given by G phi by 2 by G0, and so this for n is equal to 2, we can write G taper will be, so this value was 130 degrees. So, G of 65, so you can put it, and please remember here it will be 10 log D because it is a power pattern. So, this becomes minus 7.48 dB, n is equal to 4, G taper becomes minus 9.66 dB, n is equal to 6, G taper becomes minus 9.03 dB. Okay. So, that shows you the thing. So, we can so from this people have found out that various graphs, this whatever I have said, that aperture field in terms of actual values, if you give it in dB, then there will be difference, and this is the G taper, this is the aperture field taper for various choice of n. Okay. Then this is circular aperture illumination efficiency, that means eta x, and maximum side lobe level for aperture field. So, for a eta I how much you get. So, you see that if we take this aperture taper to be more and more, for then you see that illumination efficiency that actually falls, and side lobe level, you see that if we increase the aperture taper, the side lobe level actually goes down because this is minus 40. So, that is good. That means, if you give more taper, the side lobe falls down, which qualitatively we said earlier. So, compared to uniform distribution of the aperture field, tapered gives 25 dB reduction in side lobe typically. So, in communication I already pointed out that this side lobe reduction is more important, and so people have so that thing that you should consider that what is the efficiency you are getting. So, based on that you will have to modify the aperture illumination efficiency, that means where from we have started. Then there will be so we can, I think, from whatever we have also this thing, let me discuss that. Actually, I have a large surface, and there we are assuming that we are having a suppose polarization like this, but there will be also, because this is an aperture surface. So, there is no point of preventing this cross polarized field. So, some cross polarized field will come because there is the horn is also giving that cross polarized thing, then there are scatterings, there are various reflections on the feed, etc. So, all that gives this cross polarized thing. So, that also need to be taken, that what is that can be estimated, we are not going there. So, let us see a problem that suppose we have a 10-meter diameter reflector. Let us do a problem, a 10-meter diameter reflector with f by d ratio of 0.5, because generally these reflectors are specified like this, and frequency, operating frequency is 3 gigahertz. The feed is having a pattern which is, feed pattern is symmetrical, and given by g theta is equal to 6 cos squared theta. So, that means you see it actually satisfied our that feed optimum feed distribution that people have found. So, here n is equal to 2. So, 2n plus 1 is 6 and this is cos square theta. So, first find out what is the overall efficiency. That means, let us say other efficiencies we have. So, basically we will have to find eta as. So, first thing is we know f by d ratio, the f by d ratio is given, that actually gives us the angular aperture, because we know f by d is nothing but 1/4 cot pi by 4, and this is specified as 0.5. So, from there I can find out the phi value will be 106.26 degree. So, now we can find out eta s, because eta s is cot square pi by 4 24 sin square pi by 4 plus ln cos pi by 4 whole square. This expression I have already given earlier. So, if you calculate, you will see that this value comes to be 0.75. So, obviously, this is not an optimum, because f by d ratio is given. So, we could not choose that. If we had our thing, then we could have chosen from the graph to maximize eta s. We can find for n is equal to 2, that value would have been 130 degree, but here it is actually 106 degree. So, that is why it is coming as 0.75. Now, also I can, since the A is given, what I will say that diameter of the reflector is given. So, immediately I know what is the diameter is given and also the frequency is given. What will be the directivity? Directivity can be easily calculated, aperture directivity. Please remember, this is aperture directivity. Here you can see this is actually a paraboloid dish, this is the horn feed, you can see the horn feed here, this is the horn, this is a circular horn instead of a rectangular horn, it is at the focus, and aperture means this circular zone. Please see, this is a circle here, hypothetical circle, that is the aperture, that's diameter is being said. So, f by d ratio means this diameter by this f, the focal point distance. So, aperture directivity will be 4 pi by lambda naught square into pi a square. So, frequency is said, frequency is 3 gigahertz, that means you have 10 centimeter and A is 10 meter. So, if you put all those values, you will see it comes to be 49.94 dB. And then what will be the gain of this reflector system? Here we assume that other efficiencies are all 1, eta and eta s we have calculated. So, gain will be eta into d. So, eta is 0.75 and this gain is absolute value is 98696. So, that becomes 48.69 dB. And now, what is the spillover efficiency? Spillover efficiency, since we know the aperture, we can find spillover efficiency 1 minus cos psi by 2 n plus 1. So, that will be 0.784. So, 78.4%. And then what is the illumination efficiency? Since I know that eta s by eta s value I have found 0.75 by 0.784. So, that is 95.66% illumination efficiency. Okay. Now, there will be other efficiencies also which we have not said. One of that is the surface roughness. Actually, this surface, you see here the rays are coming. So, if the surface is having a rough surface, then there will be some error, because here we are assuming that the rays are regularly reflected, but due to the surface imperfection there will be a. So, that is specified in terms of surface error. So, any dish antenna for fabrication, actually the very critical thing in the fabrication is the surface roughness. Actually, the random error is specified, that how much surface error is a. So, in terms of that, people have found that some distribution for a random Gaussian distribution they assume, and from that there are formulas for finding the surface roughness. So, that efficiency is called eta r. Also, you see that this problem actually we will later discuss, that the rays are, look at here, this feed is getting it here, but there are some arrangement here for maintaining the feed. You see, this whole arrangement is to maintain the feed. So, this is feed and its supporting thing. Also, there will be cables from which maybe RF cables, maybe a waveguide here. Now, the problem is, after this thing gets reflected, the reflected ray, this feed is blocking that. So, some portion of the power is not going to the thing. That is one thing. Also, another thing is, suppose this thing, the paraboloid reflector is looking at top, suppose to a satellite, but the feed is looking to the ground. You see, so feed has below this paraboloidal surface also, it is receiving signals from here. So, lot of ground reflected noise it catch. So, that will reduce the sensitivity, but before that this efficiency that will be mattered, because this feed is blocking this, that is called blockage efficiency. So, one was spillover, that all the power was not captured. Now, whatever is being reflected, the feed and its accessories are blocking that. So, there will be another thing which is called eta b, this is blockage efficiency. So, finally, I write that what are the efficiencies that is involved in the aperture efficiency. So, that will be, one is spillover efficiency, one is illumination efficiency, one is polarization efficiency, one is uniform field efficiency, then this surface roughness, this is surface error, surface I will say roughness error efficiency, and then the blocking efficiency. So, all this affects the aperture efficiency. So, finally, gain is nothing but eta aperture efficiency into the directivity of the aperture. Okay. With this I conclude. In the later we will see that some of the techniques for by which this blockage thing can be tackled. Thank you.